Hello, everyone. So we continue with the explanation of the Lemke Howson algorithm. So I'm going to share with you some lecture notes, which is Appendix 1 um, from lectures 6, 7, and 8. Hopefully you see the PDF file. So what do you have here? Here I detail some of the main steps of the Lemke Howson algorithm. So the first part is about an introduction, general introduction to the Lemke Howson algorithm. Generally, what it says, in fact, if I can summarize, to be able to run the Lemke Howson algorithm on a small Bimatrix game, we need first of all to do some pre-processing, and we'll understand what you need, what we mean by pre-processing. Then we have to perform some initialization of our tableaus. Third and main step, which is repeated pivoting, and four, recover the Nash equilibrium from the final tableaus we got. So first of all, step one, what is pre-processing? Recall what we have seen in the first part of the lectures, 1, 2, 3, or 1 and 2, where we talked about strictly dominated strategies. And here you need to run your Bimatrix game through some strictly dominated strategies, pre-processing, and eliminate them. And this would generally reduce the size of the Bimatrix game. Okay, so, and second thing with the pre-processing, as we said in the previous video, the Lemke Howson algorithm works only with positive matrices, positive payoff matrices. So you need to add the absolute value of the minimum value of the minimum entry in each payoff matrix to every entry to obtain matrices which are strictly positive or just positive. Okay, so then we need to go to step 2, which is the initialization part. The initialization of the tableau, which starts from this system where you have AY plus R equals 1 and BTX plus S equals 1. And this is what we developed in the previous video, what we inherited from the dual linear programs. Okay, so explicitly on the following Bimatrix game, which is 3 by 3, I write here the two initial systems. The first one is for R equals 1 minus AY, okay? And you can follow up here. And here, S is equal to 1 minus BTX. So these are the two initial systems, okay? So once we are set, we can start pivoting. And to start pivoting here, at the opposite of the simplex algorithm or the dual simplex algorithm, with the Lemke Howson, you need just to do some arbitrary initial move. The first move is always arbitrary, so you can pick whatever entering variable. And once you pick the entering variable, everything will come automatically. So here in this case, what did we pick? We picked just x1 to be the entering variable, and using the minimum ratio rule for the leaving variable from the basis from the second system, which writes S equal 1 minus BTX, the minimum here would be given by S4. The minimum new value for x1 would be 1 over 2. So if x1 enters here, S4 leaves the basis. And everything rolls from there. If S4 leaves the basis, what you could do is to make Y4 enter the basis, because now you don't forget that you have these linear complementarity slackness conditions. And you will have, of course, Y4 times Y4 equals 0. Since S4 became 0, you can make Y4 non-zero. And that's exactly what it is said here. So what happens in the next page? X1 entered the basis, and you can put this in the tableau, in the simplex tableau if you wish, avoiding to write it as a linear system. And we did it in class quite easy. And we did it on the tribal conflict problem, in fact, and I uploaded the solution on the Blackboard. Once you did the first pivot, so this is x1 expressed in terms now of the non-basic variables in its own system, and y4 also enters the basis, and if y4 enters the basis, you can go back here and see that the minimum value for y4 would be the minimum between 1 over 1 and 1 over 2, so for sure R3 would leave the basis, and that's why Y4 took the place of R3. Okay, and if R3 leaves the basis, you can make X3 enter the basis. And that's what it says here. Since R3 left, now X3 enters the other tableau. So from here, you can see that if X3 enters the basis, the minimum would be the minimum between 1/2. Here, there is no X3 in the second one, and here 1/3. Okay, so if X3 enters the basis, it would take the place of S6. And this is what happens now in my system. X3 is equal to 1/3 minus 1/3 of X2 minus 1/3 of S6. And you can substitute back. It's easy to do in the tableau format. Okay. And since S6 left, Y6 can enter the basis. And this is basically, you come back here and you can check that there are two possibilities. Either the minimum ratio will be 1/2 or the 1/2 or 1/2 is 1. So basically R2 would leave the basis. And if R2 leaves the basis, so this is what happens here. R2 left the basis and Y6 entered. And this is when, this is what happens when X2 entered the basis. Here, since R2 left, now X3 enters. Okay, so the minimum ratio is given by S6. And that's it. So X3 entered here. And since X6 left, Y6 enters. And this minimum ratio is given by R2. So this is the substitution. Y6 took the place of S6. And here, since R2 left, now X2 can enter the basis by the minimum ratio rule. And S5 leaves. So at this stage, what you can see is that all the X's and the Y's are non-zero. For sure, this would mean automatically that we have reached the Nash equilibrium, because all the XR, YS conditions are now equal to 0. That's for the complementary slackness conditions. Okay, so we are pretty much done with step 3. Okay, now, does it mean that in the Nash here equilibrium, you have these corresponding values for your strategies? This is the way the players 1 and 2, they formulate their strategic play? No way, because if you sum up the X's and the Y's, no way you can get 1s here. And to get the Nash equilibrium strategies, you need to sum up the values of the X's. And every X played is equal to the corresponding value found in the final tableau, of the Lemke Howson algorithm, divided by the sum of the X's. Similarly, for the Y's, the corresponding value in the Nash equilibrium is equal to its value here in the final Lemke Howson tableau divided by the sum of the Y's. And which means that you can get the following Nash equilibrium, which gives you X1 equals 6/13, X2 3/13, X3 4/13. You can see that the sum is equal to 1. And Y1 is equal, or Y4 is equal to 1/9, Y2 is equal to 3/9, and Y6 is equal to 5/9. Here, we have used this indexation X's going from 1 to 3, and Y is going from 5 to 6 to avoid any confusion between the subscripts. Otherwise, everything is okay. Also with the formulation you've seen on the slides. So I hope this is clear, and hopefully we'll get back to you soon with another video. Thank you very much.